Today's video is going to focus on what we call an atom inventory and balancing chemical reactions. This is one of the true hearts of chemistry, where we're going to talk about how chemical compounds and elements, no longer looking at their individual properties, but how they chemically react and combine together with each other to form new compounds and new materials. And so there's a couple of terms that we want to highlight here at the beginning. First off, a chemical reaction is when one or more substances changes into a chemically new substance. So not something like ice melting into water or water boiling into steam. Those are all still chemically H2O. In a chemical reaction, the actual atoms that are bonded together change what they're bonded to and turn into something entirely new. And so the two terms that are connected closely to this is a reactant and a product. And the reactant is the beginning substances before a chemical change. So the materials that we're going to be putting into the reaction, and then the product is what we produce. So the product of the chemical reaction, of the substance formed after a chemical change. And so on the right here, we see an example of a chemical reaction, and the materials that we have to the left side of the arrow is our reactants. These are the things that we're going to combine together, just like an addition. Copper plus silver nitrate are going to combine together, and then this arrow is what we call the reaction arrow. And then on the right side of that arrow are the products of that chemical reaction. So we have reactants on the left and products on the right. And that's pretty standard practice. You've seen this before when we did our unit on nuclear chemistry, where we had the nuclear material on the left side, and then the alpha particles, beta particles, gamma particles on the right side. So the process is still very much the same. We're looking to account for the fact that the same amount of material going in and the same amount of material is coming out. Just like in a nuclear equation, we wanted the number of protons and neutrons going in to match up the number of protons and neutrons coming out. And that's really the cornerstone of all we've really been talking about, is that in all chemical reactions, the number of atoms of each element is conserved. And we refer to this to the law of conservation of matter. What we studied before, nothing new. But this is really the true rationale as to why this process is going to be important when we try to balance everything out. And so if we look at this example off to the right, we notice that we've got one copper, one silver nitrate, and then on the product side, we've got a silver atom by itself, and then that's plus we have copper 2 nitrate. Just by inspection, it doesn't really look like this makes a whole lot of sense, because it shows that we've got one NO3 going into the reaction, and then somehow we've got two NO3s coming out. And so the example that I always use is like, boy, it'd be really nice if every time you deposited $10 into the bank account, you could take $20 later out. So we can't put in some material and then expect it to just double on its own. So there's a rationale for what we're going to look at here to make sure that the number of atoms of an element going in are the same as the number of atoms of the elements coming out. And so the first thing that we're going to practice is what's called an atom inventory. And so an atom inventory has some pretty specific steps. So to be able to ensure that all atoms are conserved, we use an atom inventory. And so the first thing that we're going to do is, under the arrow of the chemical reaction, write each atom from the chemical reaction in list form. So just like column straight down the line, what elements are we actually working with in the reaction? If there's a polyatomic involved, we're going to write it as such unless it's not present on both sides of the equation, and we'll see an example of that going forward. And then on the left side of the atom list, we're going to write the number of each atom that's present on the reactant side. And on the right side of the atom list, we're going to write the number of each atom that's present on the product side. So the actual atom inventory is kind of like step one of the whole process that we're going to be doing going forward. And so the first thing we're going to do is, under this arrow, write all of the components. So we've got copper atoms, we've got silver atoms, and we've got the polyatomic NO3 nitrate, that nitrate group, common on both sides. So we can count that as like one big group. That's the same on the reactant side and on the product side. So to complete the inventory, we do just that. We take an inventory. If you've ever had to stock shelves at a grocery store, They want you to count up how much of each, grocery item you have so that they know what's in their inventory. So on the left side of your inventory, we're going to go through this and say that we've got only one copper atom. So we're going to count it as 1. We've got only one silver atom because there's no number after Ag. And then NO3, we see no parentheses, so there's one NO3 group. So we've got one of each of those in our inventory on the reactant side. For the product side, we're going to repeat the same process, but we got to be careful because they've now switched their position, so they're going in a different order. So the number of copper atoms here is still only 1 because we don't have a number after that Cu. The number of silver atoms, again, is 1. But this time we've got now, in parentheses, NO3 with a 2 on the outside. So that means that we've got 2 nitrates on the product side of our reaction. And so by doing an accurate inventory, we're able to tell whether or not a chemical reaction is balanced. According to this, 1 NO3 went in and 2 came out. That's not a balanced process. So there's something that we're going to have to do once we practice this inventory step a little bit further to actually balance out this whole reaction. And so let's move on to the next 2 examples. Like we've done before, I'd encourage you to pause the video here, practice doing an inventory so we can get used to counting the number of each atom present on both sides. And then once you've got them both done, go back and play the video and see how well you did. All right, so just like we do with our inventory, we're going to write a list from left to right of all the elements involved in the reaction. So we've got gold, we've got sulfur, and we've got hydrogen. And on the left side, we've got 2 Au atoms, 3 sulfur atoms, and 2 hydrogen atoms. On the product side, we've only got 1 gold atom, 1 sulfur atom, and 2 hydrogen atoms. So in terms of a balanced system, again, this is not balanced. We put in 2 gold and we lose 1. We put in 3 sulfur and we lose 2. So there's some imbalance here. And we, again, are going to go through the process later on of what we can do to correct this reaction so that it produces a balanced system. Okay, last inventory we're going to practice here down at the bottom. We've got sodium, Na, but in 2 sources, so we're going to count it once. We've got silicon, and we've got fluorine. So the total sodium count on the reactant side, this is now split into 2 parts, but the total sodium count is 1, 2, 3. The total silicon count, because there's no number after that silicon in this reactant, is 1, and the total fluorine count is 6. On the product side, after this chemical reaction has occurred, we've got 1 sodium, 1 silicon, and 1 fluorine. Again, the inventory is our sure indication of, is this balanced or not? If we put 3 atoms in and we only get 1 atom out, there's some imbalance here in this chemical reaction. And all this really means is that the numbers that are involved, we can't really change, but we can augment the amount that are being produced. If we have 3 sodium atoms coming in, then there's likely that we're going to produce 3 times the number of that product because we have that many reactant atoms going into the process. And that's what we're going to talk about next on the second page. So the actual part of balancing, again, looks like it's got a lot more steps. But step number 1 is something that we've already practiced. We need to perform an atom inventory. And really, we're just getting comfortable with the counting of the atoms in a chemical reaction. So by using an atom inventory, we can add coefficients to compounds or atoms to ensure that atoms before equals atoms after. And again, that is like the big fundamental piece to this whole process. We want to account for the fact that the number of iron atoms going in and the number of iron atoms coming out are in fact the same. And so I wanted to talk a little bit about this term here, coefficient. Just like in math class, you have coefficients in front of variables. So if we had something like 12 equals 4x, the coefficient is that number 4, which I now see is really difficult to read on this blue font or this blue background. But a coefficient is just a multiplier. So 4 times x equals 12. What would x have to equal? Okay, that's 3. What we're looking to do here is put multipliers in front of a reactant or a product to increase the number of that element going in or coming out of the chemical reaction. Okay, so we're going to follow these rules, perform an atom inventory. Remember that polyatomics act like a single unit, all grouped together. And then starting with the unbalanced elements, begin by balancing by using coefficients. Okay, you never try to balance by changing the subscript in a formula. Okay, we can't just make something H3O because we need another hydrogen so that our reaction is balanced. H3O does not count. All right, it's H2O. Once a coefficient is added, we then have to change the recorded number in the atom inventory. So every time a multiplier goes in, we have to go through and update our count for that particular element or elements, and then check each atom or polyatomic to make sure the equation is balanced. And then lastly, make sure all the coefficients are in the lowest possible ratio, because there are multiple answers that could be possible, but we want it to be in the simplest whole number form. So let's practice this first example up here. Right, we've got iron 3 chloride reacting with calcium hydroxide to produce iron 3 hydroxide and calcium chloride. First thing we want to do is perform our inventory. So we've got iron atoms, we've got chlorine atoms, we've got calcium atoms, and then we've got in parentheses that polyatomic hydroxide, so we can count that as like one complete set. So we don't have to look at individual oxygen atoms and individual hydrogen atoms. So the total iron count on the reactant side is 1. The total chlorine count is 3. Calcium, we've got 1. Hydroxide, 2. And then on the product side, after these things have rearranged, we now have 1 iron, 3 hydroxide, 1 calcium, and 2 chlorine. So again, our inventory here shows that we've got 1 iron in, 1 iron out. So technically our iron atoms are balanced and our calcium atoms are balanced, but the chlorines are losing 1 and the hydroxides are gaining 1. So these compounds, again, are combining, not just one at a time. It looks like there's just one of each, but we've got a whole, like if we did this reaction in a beaker, we've got thousands and thousands of each of these compounds that are combining together, and we're trying to figure out what's the ratio, how many of each are going to combine together so that these products will form in a complete whole number ratio. So the first thing we want to do is pick an element that isn't balanced. We've got 3 chlorines in, 2 chlorines out. So what multiplier could I put in this blank and this blank so that the number of chlorines goes to the lowest whole number? That would have to be 6. Right? So if I put a 2 here and a 3 here, that 2 is going to act like a multiplier and say 2 FeCl3s are giving me a total of 6 chlorine atoms, and that 3 is going to act as a multiplier and give me a total of 6 chlorine atoms on the product side. So now what we want to do, anytime we put a number, we need to update our inventory on that respective side. So if I have 2 FeCl3s here, that means that I now have 2 iron atoms, 6 chlorine atoms. Okay, and now by doing this, it does throw my iron numbers off, but this whole process is what I refer to as like a ping pong method. You kind of bounce back and forth and complete the set until everything is balanced out. So you might be throwing something that was perfectly balanced out of alignment in the process. That's okay. We'll get there in the end. Right? So then we have to update the inventory here on the product side. We've got a 3 in front of calcium chloride. So that means we now have 3 calciums, and then multiplying across, we've got 6 chlorines. So we took our imbalanced chlorine numbers, and we've now got them balanced, 6 going in, 6 coming out. Now we've got 3 other elements that aren't balanced, and really we could pick any one of those as our next starting point. Okay, so if we pick iron, we put 2 irons in, so we would have to put a 2 here to get 2 irons coming out. Right? So now if we update this inventory, that means that we've got 2 irons on the product side and a total of 2 times 3 or 6 hydroxides on the product side. Okay, so now our iron and our chlorine are balanced, and we've got this one number that we could put here that would give us 3 calcium on the reactant side, and lo and behold, we got 3 times 2, 6 hydroxides on the reactant side. So now we know we've got a completely balanced system because 2 irons are going in and 2 irons are coming out. 6 chlorines are coming in, 6 chlorines are coming out, 3 in, 3 out, 6 in, 6 out. So this is what we're looking for a correct final answer. The number of elements on our reactant side in some specific ratio matches up to the number of elements of that on the product side. Okay? So again, let's pause the video here. There's 3 other example problems on the page, which I would encourage you to practice out on a separate sheet of paper. And then once you've gotten those and you think you've gotten a good idea, play the video, walk through the examples with me, and then we'll practice this for your homework. Okay. All right, so if we've got an unbalanced reaction here, we're going to start always by doing an inventory. We've got silver atoms. We've got this NO3 group here, so we can count NO3 nitrate as one common thing. We've got hydrogen on both sides, and we've got sulfur on both sides. So to perform our inventory, we look and see that we've got 1 Ag, 1 NO3, 2 hydrogens, and 1 sulfur. And then on the product side, we've got 2 silver, 1 sulfur, 1 hydrogen, 1 nitrate. So most of these are balanced. Our NO3 and our sulfur are balanced. It's the silver and hydrogen that are not. And you can pick any of the unbalanced components as your starting point. So we could start down here with the hydrogen and say, if I'm putting 2 hydrogen in, I need to get 2 hydrogen out. Okay, so I put a 2 up here to give me 2 times that 1 hydrogen. But now I've got 2 hydrogens to balance and 2 nitrates coming out. And then if we pick either one of these, which are now also imbalanced, 1 in and 2 out, we can start with the nitrate, which was balanced and we just threw off, and we could put a 2 here to multiply through and give us 2 nitrate, and as a result, it's also giving us 2 silver. Okay, so now our balanced inventory is showing 2 in, 2 out, 2 in, 2 out, 2 in, 2 out, 1 in, 1 out. So this is what we're looking for a final balanced inventory. And the coefficients up here, a couple of them are blank. And so we can actually leave those blank, or if you're somebody who has to have like every box filled in, you can put a 1 because a blank is kind of like an understood 1. So we've got 2 silvers, 2 nitrates, 2 hydrogens, 1 sulfur, 2 silvers, 1 sulfur, 2 hydrogen, 2 nitrate. So those coefficients, those ratios, 2 of this compound and 1 of that compound are combining together to make 1 and 2 products on that side. Next example, we see we've got 3 products, and we've got some chlorines in multiple spots, so we have to look and take into account the fact that the chlorine numbers are present in 2 areas. And we've got 2 reactants on the reactant side. Same process as before. We're going to start by doing our inventory. So we've got manganese atoms, oxygen atoms, hydrogen atoms, and chlorine atoms. And if we do the inventory on the reactant side, we've got 1 manganese, 2 oxygen, 1 hydrogen, 1 chlorine. And on the product side, we've got 1 manganese, 1 oxygen, 2 hydrogen, and 1, 2, 3, 4 total chlorines. Even though it's split over 2 products, the total chlorine count on the product side is 4. So again, we can pick any of the unbalanced elements in our inventory as our starting point. There isn't one particular benefit to starting with one element over the other. We just wouldn't start with something that's already balanced because there's nothing to work with. All right, so if we start with the chlorine, we have 4 total chlorines on the product side, which means we're going to need 4 times this particular chemical to get that many chlorine atoms going into the reaction. That means that we're going to have 4 chlorines and 4 hydrogens after we multiply that with a coefficient of 4. And if we have 4 hydrogens going in and only 2 coming out, then that extra hydrogen is going to produce extra water molecules, and that multiple of 2 is going to give us 4 hydrogens and 2 times 1, or 2 oxygens. So just by putting a 4 and a 2, this completely balances out that reaction, which looked a little bit more menacing than what it actually was. right? So we get 1 in, 1 out, 2 in, 2 out, 4 in, 4 out, 4 in, 4 out. This is a completely balanced chemical equation. So 1 manganese 4 oxide plus 4 hydrogen chlorides will produce 1 manganese 2 chloride, 2 water molecules, and 1 chlorine molecule. Okay, last example, and this is a common type of a chemical reaction that we commonly call a CHO reaction, because the atom inventory only involves these 3 chemicals: carbon, hydrogen, and oxygen. All right, this is one of the major categories of a type of reaction, which we're going to get into at a later video. But these oftentimes produce a little bit more concern for my students because we, again, have oxygen in multiple parts and the numbers can get kind of large. Don't get thrown off by some chemical reactions where the coefficients will sometimes be like 14 and 16. A lot of times, certain chemical reactions require a large consumption of oxygen, and these coefficients can really get kind of large. Right? So if we do our inventory, on the left side, we've got 3 carbons, 8 hydrogens, 2 oxygens. But on the product side, we've only got 1 carbon, 2 hydrogens, and 3 oxygens split over both products. Right? Now, this one usually has one particular preferred method. If you start with the oxygen, we could figure out what coefficient is going to get us the number of oxygens going in and the number of oxygens coming out. But it's a little bit more beneficial to start with the carbon and the hydrogen, because no matter what, if I have 8 hydrogens going in, there's going to have to be a number or a coefficient on this blank. And that means that it's going to multiply by that oxygen number, and the carbon is going to have a coefficient which is going to multiply that oxygen number. So a lot of times it's often better to save the elements when they're by themselves like this for the very last step. So we can put whatever number we need here, but the carbon and the hydrogen are going to throw off the product oxygen count. Okay, so let's start by balancing out the carbon. If we have 3 carbons going in, we want a multiple of 3 there so that we have 3 carbon atoms coming out and 3 carbon dioxide molecules. So now we've got 3 carbons and 3 times 2, a total of 6 oxygen plus that 1. So we now currently have 7 oxygen atoms on the product side. And then we're going to balance out our hydrogen. We've got 8 going in. We want 8 coming out. This time we're going to put a multiple of 4 because water has 2 hydrogen atoms per molecule. So we're going to produce 4 times the number of water molecules to give us, again, 8 hydrogen atoms. But our oxygen numbers are thrown off again. 6 from the 3 CO2s plus 4 from the 4 H2Os. So if we have 6 oxygens here, 4 oxygens here, we now have a total of 10 oxygen atoms. And there's a number here that's a nice multiple of 2. If we've got 5 O2 molecules, that means that we then have 10 oxygen atoms going in to balance the 10 oxygen atoms coming out. Right? So the process is pretty much this, pretty straightforward. Take the time to write your inventory, count everything up carefully, and then double check to make sure everything is balanced out at the end by seeing that the number of atoms going in and the number of atoms coming out in your inventory are the same.